Is this working? This is working, right? Everybody can hear me?
Yes.
Good, good. So, thank you. I'm happy to be here. Thanks for inviting me, Seymour, and everybody else. I wanted to talk about work joined with, I'm going to be using the blackboard. That's a bad idea. I can turn on the front lights, I guess. I'm talking about work joined with Maria Tarnowski on well, as it says on the title. But I understand that I shouldn't assume any graph theory. And so I'm going to spend a fair amount of time on background before I get to the real theorem, I think. And that is probably better to do on the blackboard. So half of this talk is going to be on the blackboard and half is going to be on the transparencies. Sorry. So let me start with the blackboard. Maybe out here. You know what a minor of a graph is? H is a minor of a graph G if H can be obtained from a subgraph by contracting. And the theorem, the well-known theorem about minors that everybody learns when they're starting graph theory is the Kuratowski-Wagner theorem. That a graph is planar if and only if it has no K5 or K33 minor. So I really don't know how much you know. Does everybody know what this says? Do you understand? Do you know what K5 means and K33 means and planar means? K5 is the graph with 5 vertices all joined to one another. K33 is 3 vertices and another 3 vertices, and these are all joined to these 3. And planar means you can draw it in the plane without any edges crossing. So, for instance, if I took here's almost a drawing of K5. This is almost K5, but I need one more edge. If K5 with one edge removed is planar, K5 itself is not. But this is a famous theorem from the 1930s, I guess, that characterizes planarity. And it's surprising that you only get it's enough to list 2 graphs. Just 2 graphs. What's special about these graphs? That they're the minimal graphs that are not planar. The minimal graphs, minimal undertaking minors, with the property that they're not planar. So the only graphs, minimal on the minors, not planar. And there are other theorems of the same type. So there's a theorem that of the archdeacon that says a graph. So you can draw graphs in other surfaces, not just the plane. You can draw graphs on the torus, or you can draw graphs on the Mobius band. You can draw graphs on different surfaces. G can be drawn in the Mobius band You know what a Mobius band is? You take a rectangle and you twist it and join it up. You know what that is? Do you know what drawing on a surface means? You think about it, you probably don't, because I mean, there's a difference between drawing with a pencil and drawing with a knife. If you draw with a pencil, you might also draw something else on the other side. That's not fair. You draw with a knife, it goes through. If you draw on this side, you've also drawn on that side. Both sides are used, right? Anyway, never mind. It can be drawn on the Mobius band if and only if it has none of not just 2 minors, but 35 minors. And I won't tell you what they are, but you can listen. They're not. And these graphs, whatever they are, the H1 to H35 are the only minimal that cannot be drawn on the projected, cannot be drawn on the Mobius band. And it's the same thing. And there's another. Which graphs can you draw in 3 space now? But with, I mean, you can draw any graph in 3 space. You put the vertices down, if every edge is to be represented by a line, you can just put it in, right? In 3 space. It's easy. But what if I want to draw a graph in 3 space such that no 2 cycles are linked? For some curious reason, maybe I would like to do this. When can I draw a graph in 3 space so that no 2 cycles are linked? And there's a list of that. There's let's call them J1 to J7. There's 7. The only minimal graphs not linklessly embeddable in 3 space. And the point is that they're known. These graphs are known. But there are lots of other theorems of the same kind. You can think of a property. You can figure out the minor minimal graphs for that property. You can find them all. Now, on the list, there's 2 here. There's 35 there. There's 7 there. It's always finite. And that's the point I want to get to. And in fact, it's a theorem of Robertson and me, Neil Robertson and me, that for any property, you always get a finite list. That for any property of graphs, you list the minimal graphs that don't have the property, and the list is always finite. For any property P, the set of minor minimal graphs without property P is fine. That's a hard theorem. That's the so-called graph minus theorem. It took us 20 years to prove and 20 papers to prove, and they're big papers as well. This is long and hard. You may think this is a strange way to say it. Another more, should I get rid of this? Let me get rid of this for a little bit.
Yeah. You wanna, yeah.
This one?
No. On the,
over here?
yeah. This up. Yeah.
Maybe a mistake. I'm probably about to use transparency again. Another way to say it is that for any infinite set of graphs, one is a minor of another. One of the graphs in the set is a minor of another. This is the same as that. because if you believe, is that clear? You take the minor minimal graphs without a property, it's some set of graphs, and what you know is no one of them contains another because they're both minor minimal without the property. They both don't have the property and the minors do. So none of them can be a minor of another. And vice versa. If you have an infinite set of graphs such that none is a minor of another, you construct the right property. What's the property? Suppose I knew that and I wanted to prove this, what would I do? Define P. How would you define P? The set of all, the property of not having a minor in this set. Here I have again. No. If I know this statement and I want to prove that statement, suppose I have an infinite set of graphs, no one is a minor of another. I define P to be the property of having no minor in this set. I apply that, and it ought to be equivalent. I think it better be equivalent, or else I wasted 20 years. Anyway, this is the sort of old theorem. We finished this in, I think, 1996 or so. But it's done now. And there are a lot of applications. You know, maybe I don't want to really go into the applications, but there are a lot of nice consequences that how can you prove a thing like that? That the way we did it was, suppose it's false. Well, it's first of all helpful to, let me tell you what a well-quasi-order is. Let me tell you what a well-quasi-order is. It's as far as we are concerned, it's a partial order. I mean, there's a slight difference between a quasi-order and a partial order, but it doesn't matter. Partial order, less than, such that for every infinite sequence, let's say Q1, Q2, Q3, there exists I less than j, such that Qi is less than or equal to Qj. So for any infinite sequence of elements of the partial order, not only does there exist two terms so that one is less than another, there exist two terms, one less than another, where the later one is later in the sequence. It's a little bit different. It's actually equivalent, but this is more convenient to work with than that statement. And we're proving that the set of all graphs is a well-quasi-order under minors. Right? For any infinite sequence of graphs, there's a graph and another graph such that this is contained in there. That seems to be a little bit stronger, but it's really this statement is equivalent to that one. It's not hard. The nice thing about working with well-quasi-orders is it's easy to make more complicated ones starting from simple ones. So for instance, if you have a well-quasi-order, say Q1 less than 1, and another one which is Q2 less than 2, then you can define a product. We'll look at all terms, the entries of Q1 times, so all pairs, where the first term is in Q1 and the second term is in Q2. So say I have xy and I have x prime, y prime, where x and x prime are in Q1 and y prime are in Q2. Now I wanted to find an order on this. And you do it component-wise. We'll say that's true, that means x is less than x prime in the first quasi-order and y is less than y prime in the second. So it's just, you take a product of two orders like this in the natural way, just the component-wise product. There's a theorem that if this is a well-quasi-order and so is that, then so is this. if that, then this, with that product, is a well-quasi-ordering. Which is, you can combine them. And there's also a theorem, maybe I'll show you later, that finite sequences of different lengths also, let me tell you now, I know what's up. There's a theorem that, this allows me to compare pairs. If I have a quasi-order Q less than, I can now look at Q cross Q because of this. And similarly, I can look at Q cross Q cross Q. And this allows me to compare triples of entries. But I can also define sequences of different lengths. So I could take a sequence x1 to xk and y1 to yl. And under certain circumstances, I'll say this is less than that. Meaning, there's, so think of, here's x1, x2, x3, up to xk. Here's y1, y2, up to yl. I'll say this term is less than that one if you can make an injection, an order-preserving injection, such that, so x1 will go to y, I1, x2 will go to y, I2, x3 will go to y, I3, and so on. If there's an injection like that where h is less than y, I sub h for all h. So if the small sequence can be mapped into the big sequence in a term-by-term way. Is that clear? It doesn't really matter, but I thought I'd do it now while I'm on the topic. This is the hard theorem of Hickman that if Q is a well-quasi-order, then so is the set of all finite sequences over Q. Ordered this way. But let me not prove it. Maybe you could, it would take 5 minutes to prove it, but let me not. Well, let me get back to graphs. How can you prove a thing like this? The idea is, suppose it's false, then there exists a sequence, an infinite sequence of graphs G1, G2, G3, such that Gi is not a minor of Gj for any I less than j. Right? If the theorem's false, then there's an infinite sequence where no term is a minor of the later term. But actually try and construct that. I mean, when you get lost, even when you get lost, try and disprove this, because it's kind of fun to try and actually do it. You can do it. Just make a sequence of graphs. You always end up where a later graph contains an earlier graph. Anyway, so suppose we have a counterexample. Then, in particular, they don't contain G1. So G2, G3 do not contain G1. Just very special. What do the fix a graph G1. What do the graphs look like that don't contain it? I mean, here we're starting with general graphs, but now they don't contain G1 as a minor. What do the graphs look like if they don't contain G1 as a minor? Depends on G1, but there's something you can say independent of G1. All graphs not containing G1 have a certain restricted structure that almost, they break at small cut sets into pieces that are almost of bounded genus. They're almost head-on surfaces. I'm not going to tell you the theorem exactly because it's complicated. But there's a structure theorem that describes the graphs not containing a fixed graph. Fix any graph and look at the graphs that don't contain it. They have sort of bounded genus. It's a lie because you can glue them together at small cut sets, but apart from that, well, it's a lie in 2 or 3 different ways, but essentially they have bounded genus. There's a bound on their genus. They go into fixed surfaces. Anyway, it doesn't matter what that theorem says. This is all background. But the method is we were trying to get a contradiction from this. We were assuming our main theorem is false, trying to get a contradiction. And now we're done. We can apply this structure theorem. So that tells us that all these graphs have this structure because they don't contain G1. So instead of a bad sequence of general graphs, we now have a bad sequence of graphs, all of which have some fixed structure. They're all on the surface. They're all on the same surface. It's an infinite sequence of graphs all on the same surface. And that helps. I mean, the graphs are now much more under control. Instead of an infinite sequence of general graphs, you've got an infinite sequence of graphs all on a surface. I mean, I've simplified it too much, but something like that. Let me get to the point. That was background. Let me tell you the new theorem. Now, more recently, in the past 10 years, I've been working on induced, I didn't tell you what induced subgraphs are. Let me tell you that. So, I told you what it is for a little graph to be a minor of a big graph. Oh, sorry. I told you what it is for a little graph to be a minor of a big graph. Now I want to tell you a different kind of containment. We'll say that a little graph is an induced subgraph of a big graph. Well, first of all, H is a subgraph. But, so a subgraph means you keep some of the vertices and you keep some of the edges, and you're allowed to delete stuff. To be an induced subgraph, you keep some of the vertices, and you look which of those vertices are adjacent in the big graph. You have a big graph, you choose some of the vertices. Now some of them are adjacent, some are not. If they're adjacent in the big graph, they're also adjacent in the little graph. Let me give you an example. Say G is, let's say this graph. And then H is that. So this is a subgraph of that. You can see it on these 4 vertices. But it's not an induced subgraph, if I did it right, because however I choose 4 vertices here, I don't get exactly that. If I choose these 4 vertices, I get that. Right? So it's a subgraph, but it's not an induced subgraph. So this is quite a different containment relation on graphs. This is not a well-quasi-order, unfortunately. I mean, being a well-quasi-order made the minor relation for graphs very successful. There are a lot of good theorems about minors, and I think that's partially because it's a well-quasi-order. This is not a well-quasi-order. For instance, if you take this sequence of graphs, just cycles at different lengths, then it's an infinite set of graphs, and no one of them is an induced subgraph of another. No one is even a subgraph of another. So that's unfortunate. We would like to prove something is a well-quasi-order. We're working on induced subgraphs, and we would like to prove that something is a well-quasi-order. Unfortunately, it's not true, so we have to do something. conjecture of Rao from about 1980. Suppose they take so I need to tell you what a degree sequence is. If I get a graph, then for every vertex has a degree. The degree of a vertex just means the number of edges at that vertex. So this graph has degrees 5, 3, 3, 3, 3, and 3. Right? And that's the degree sequence of a graph. The conjecture is that if you look at degree sequences of graphs, they are well-quasi-ordered. And I have to tell you what containment means. Containment will say a degree sequence is contained in another when I go to the degree sequence, I've lost information. There can be several different graphs with the same degree sequence. But we'll say that this degree sequence is less than that one. And if I can choose a graph for the first degree sequence and a graph for the second degree sequence, such that this one is an induced subgraph of that. It's not even clear that this is an order. This is a partial order. I mean, you can prove in a couple of minutes that this is a partial order, but you need to think a little bit. It's not even clear it's a partial order, but it's not only a partial order, but it's a well-quasi-order. And that's the theorem I want to tell you. So where are we? Here are 4 theorems. Let me explain what all these theorems mean. So the top one is the one I already told you from the old theorem of Robertson and myself. The second one is the new theorem, Rao's conjecture. And now here are 2 more. Now what are these to do? This 4th one is related to the second. It turns out to be what we need to prove the second. And the 3rd one is like the 4th one, but easier. So instead of proving the 4th one, I was going to prove the 3rd one because it's easier to prove than the 4th one, and it's a bit similar. Now I have to give you another stack of definition. You understand everything about the first 2 boxes? Please ask if you don't. Is everybody happy with the first 2 boxes? Now, let me tell you what the third, so what is a tournament? A tournament is you take a complete graph and you put directions on all the edges. So for instance, oops, thanks. How did you do that? Okay, very clever somebody. So a tournament is, you take a complete graph and you direct the edges somehow. So it's a directed complete graph. And what does immersion mean? So I should tell you when a directed graph is immersed in another directed graph. So let's call this one H, and here's a bigger directed graph G. What does it mean that H is immersed in G? Each vertex goes to a vertex here, but there are many more vertices. Right? So for each vertex you choose a vertex. And for every edge you choose a path between the vertices. So here is a path. A directed path. Except the paths can intersect. The paths are permitted to intersect. They can share vertices. They must not share edges, but they can share vertices. And it would be more natural if they couldn't share vertices, but then it doesn't work. So we permit them to share vertices, except I cannot draw it. So for instance, I might do that. Right? But for every pair of vertices you get a path, and the paths can share vertices, but not share edges. That's immersion. The theorem is the set of all tournaments is well-quasi-ordered by immersion. Now this seems to have nothing to do with Rao's conjecture. The red theorem is halfway in between. Let me tell you what this says. Sorry. This is contests. A contest is the same thing as a tournament except with a complete Pythagorean graph. You take a complete Pythagorean graph and again direct all the edges. So you put directions on the edges somehow, you won't direct all these edges, but every edge gets an arrow. That's a contest. And again we do immersion. Except here, contests have a left side and a right side. So for a little contest to be contained in a big contest, I want left side to go to left side, right side to go to right side, and then paths. Alright, so that's four theorems, and I would like to vaguely tell you how they're related and how it fits together.
That's the ninth one.
What?
That's actually something to do with the usual.
Yeah, I guess it's you have people fighting each other or competing against one another, and then you put an arrow if this person beats that person. And there should be another name for a set of people and another set of people, and each of these plays each of those. But really, I think that's called a tournament, isn't it?
It looks like
What?
it's legal. I think tournament is like legal.
Anyway, let me give you some idea how this goes. So let's try and prove the second statement. So Rao's conjecture.
The method by degree sequence, does it actually matter? It doesn't matter which order the vertices are in?
It doesn't matter. I mean, it's just an isomorphic graph if I switch to those. Let me see. Suppose I would like to get graphs back in. I don't want to work with degree sequences. I want to work with graphs. So I would like to interpret the Rao's conjecture in terms of graphs. Let me say that a big graph switching contains a little graph. If I can replace the big graph by another graph with the same degree sequence, so that now I contain the little graph as an induced subgraph. So again, a big graph switching contains a little graph. If I can throw away the big graph and choose another graph with the same degrees, so that the little one is an induced subgraph. So this graph switching contains that one because I can throw that one away, replace it by this, the degrees are the same, and now this is an induced subgraph of that. Another conjecture can be said in this language is just that switching containment is also a well-quasi-ordering. And let's try and prove it in the same way that we proved the graph minus theorem. Suppose we have an infinite sequence of graphs. We would like to prove that one of them is switching contained in a later one. I have an infinite sequence of graphs. I need to prove that one of them is switching contained in a later one. So in particular, we assume not. We assume in particular none of them contain the first graph. So it would be good if we could prove a structure theorem for graphs not containing a given graph by switching containment. That would be helpful. So that's the first step. And to do that, let me tell you this. Let me work up to that. So question 0 is, suppose I give you a degree sequence, where does it come from a graph anyway? I mean, some degree sequences cannot come from graphs. So given a degree sequence, when does it come from a graph? Here's a necessary and sufficient condition. That suppose I have a degree sequence. For every vertex I have a number, and I want to know when is there a graph where those are the degrees. It's necessary and sufficient that this condition should hold. And what's this condition? For every pair of subsets x and y, you sum the degrees in x, and you sum the complement degrees in y. If you know the degrees, you know also the degrees of the complement, the non-edges at a vertex, because you know the total number of other vertices. So you sum the degrees in x, you sum the non-degrees in y, and that should be, and subtract x times y, and that quantity has to be at least 0. So, do you see why it has to be at least 0? Let me tell you why. It'll be easier if I could reach. Let me try and do it again. But, So choose a point in x and a point in y. Suppose the graph exists. Choose a point in x and a point in y. They may be adjacent, they may be non-adjacent. If they're adjacent, then this contributes to the degree in x. If they're non-adjacent, it contributes to the non-degree in y. So every pair contributes to one or to the other. And therefore, since I have x times y pairs, the sum on the left has to be at least x times y. This is necessary for the graph to exist, but it's also sufficient. Also you need that the sum of all the degrees is even, which is true. Now, well, that's not what we wanted to know. We wanted to know, what do the graphs look like that don't switching contain a given graph? Here's the next step. Suppose I have a big graph and a little graph, and I hope that to have a switching containment, I need to check, I need to find an injection of the vertices of the little graph into the big graph. So suppose I tell you the injection. Suppose I tell you I want H to map there in that way. When does that work? When does that mapping extend to a switching containment? And it turns out the necessary and sufficient condition is precisely the same S function. That for every pair of something gone wrong with the photos. That for every pair of subsets here, the S function in G between these two is at least the S function in the little graph between these two. It's just necessary. I might go into the proof, but it's a nice characterization, and that's useful. Now, we're trying to understand the graphs. We're trying to understand the graphs that don't switching contain a given graph. So here's a little graph, and I've got some huge graph, and this graph does not switching contain this one. So that tells me, however, for any bijection, this bijection doesn't work. For every, not bijection, for every injection, this injection doesn't work. Now I know what stops an injection working, this condition I put here. Right? That condition must be violated. Whenever I choose an injection, there's some pair of subsets here such that this condition is violated. And now you figure out what does that tell me about the whole graph. And what it tells me is a beautiful picture. It tells me this. Let me see if I can explain it. So, never mind. The picture at the top is the proof of this, but let me abandon the proof. Let me at least try to make you understand the statement. So my big graph breaks into 6 sets, three big sets and 3 little sets. The 3 little sets have bounded size. They're bounded by a function of the little graph that we don't contain. And otherwise I have a clique, and the stable set. A clique is a set of vertices all complete to one another. Stable set is a set of vertices with no edges between. And the third set, and in this third set all degrees are bounded. The degrees in the subgraph are bounded. Or possibly it's in the complement instead that holds, but let me know. Plus there are rules about the edges between these 3 sets and the 3 big sets. Now what are the rules? I forgot. First of all, there's no edges here. This is complete to that. Between here it's arbitrary. And you can see the other rules from the notes I put on the picture. That this is is complete that, except there may be, not quite, there may be a bounded number of non-edges here. This has no edges to there, except it might have a bounded number. And this is almost complete to that, it's almost not complete to that, and so on. Everything is almost working for the bound, but they're bounded size sets that almost work. The big sets work exactly. There's a bounded number of errors in the bounded size sets. Anyway, what good is that? Well, if you just look at the left-hand side of the picture, there are no edges between this and that. This is a bounded size cut set. Now, a bounded size cut set is a great thing if you're trying to prove well-quasi-ordering. Let me show you why. Suppose, right, what are we trying to do? We're trying to prove we have a well-quasi-order. We don't have a bad sequence. So I have my sequence G1, G2, G3, G4, G5. And we're using the fact they don't contain G1. So all these other graphs, so general GI, now breaks into two parts with a bounded size cut set. Let me pretend this is a cut set. It's not really, but let me pretend it's a cut set. So this is GI now. The bound on this, the size of this intersection is bounded by a function. It's bounded by a function of G1. Right? So think of it as a pair of graphs. Think of it as a pair of graphs, the top and the bottom. Just cut it in the cut set like this. Now, if I do the tops, so I have infinitely many tops, and I have infinitely many bottoms. If I knew that the tops were a well-quasi-order and the bottoms were a well-quasi-order, I could think of this as a sequence of pairs from two well-quasi-orders. And we already talked about if you have a well-quasi-order and another, then also the pairs make a well-quasi-order. And that would work. So if I knew the tops were a well-quasi-order and the bottoms were well-quasi-order, then the product theorem would tell me that the whole graphs were well-quasi-order. You need to be careful that the graphs get assembled right. You need to fix these vertices where the overlap is, but you can do that with roots. There's only a bounded number of them. It's not so hard. So that's almost what this is telling us. This is like a cut set. In the right-hand side of the graph, it's a cut set in the complement. And if we change all edges to non-edges and non-edges to edges, it's a cut set there. And it doesn't matter. I mean, however this works, the point is the edges between bottom and top are under control. So if we can prove the bottoms are a well-quasi-order and the tops are a well-quasi-order, we win. And the bottoms are easy, they're just bounded degree. So the problem comes down to doing the tops. Now, the top remember consisted of a stable set and a cleave. And that's called a split graph. A graph whose vertex set can be partitioned into a stable set and a cleave is called a split graph. So here's a split graph. I've now turned it sideways. So the left side is a cleave, the right side is a stable set. Within a split graph, you can encode as a contest. So let me make a bipedal graph instead with the same left sides and right sides. Whenever there's an edge, I'll direct this edge from left to right. Whenever there's a non-edge, I direct it from right to left. So a split graph can be encoded as a contest. And therefore we want to prove that contests are well-quasi-ordered. We can reformulate the problem in terms of well-quasi-ordering contests. And now you look, and that's how we get on the well-quasi-ordering contest. That's why we want to prove that contests are well-quasi-ordered under immersion. You don't see quite how to get immersion, what immersion has to do with it. It's not the same as switching containment, but it's better. If you could prove that immersion is a well-quasi-order, it tells you that switching containment is a well-quasi-order, because one containment implies the other. So if we could prove contests were well-quasi-ordered by immersion, we would win. And then I can't tell you the proof of that, but let me instead try to give you some idea of the proof that tournaments are a well-quasi-order under immersion. I keep defining what a well-quasi-order is. I did these transparencies several times, several different places, and the definition of well-quasi-order keeps coming in. But never mind. So now I would like to do this. Set of all tournaments is a well-quasi-order under immersion. How would you prove that? Here's an infinite sequence of tournaments. I'd like to prove that one is contained in another by under immersion. Well, you can prove the following, that if in this tournament, none of them contain the first tournament. So that means if, say the first tournament has got k vertices. So let me look at a general tournament. If it's big in general, if it had k vertices that were pairwise highly connected, highly edge connected, you would win. If it had if there were a subset of k vertices that were pairwise highly edge connected, you could prove you would contain the first graph in the sequence. Contradiction. So every set of k vertices has low, there are some two members of it with low connectivity. And we need to understand, what does that tell us? What does the tournament look like if for every set of k vertices, some two of them have low connectivity? Here's what they look like. You can prove that you can order the vertices. Remember, a tournament is a complete graph with all the edges directed. You can prove you can order the vertices so that for every gap, nearly all the edges go from left to right. Only a bounded number go from right to left. This is actually not so hard. Well, that's nice. So here's again, I'm proving the tournaments are well-quasi-ordered under immersion. Take my infinite sequence of tournaments. They don't contain the first tournament. Therefore, all the subsequent tournaments can be ordered like this. So now I have an infinite sequence of tournaments. Thanks. I have an infinite sequence of tournaments. Here's one. There's another, getting bigger. And for each of them, wherever you cut it, the number of edges going backwards is bounded. For every cut, the number of edges going backwards is bounded. It's bounded by a function of the first tournament in the sequence. Well, let's cut them up then. Let's look at the smallest edge cuts here. Let's think of it as look at the smallest edge cuts. And we'll break them into pieces with higher connectivity. And then we'll break those into pieces with higher connectivity, break those into pieces with higher connectivity, until we can't break them anymore. Until the connectivity is big enough that we would contain G1. And when that happens, it must be too small to contain G1. So we chop them up into pieces and by bigger and bigger cuts until what's in between has bounded size. We're good at sequences. If you have a well-quasi-order, finite sequences over it make another well-quasi-order. If we knew that these pieces came from a well-quasi-order, we could chain them together and prove the whole graph as a well-quasi-order because of Hickman's finite sequence theory. You have to be a bit careful to get the linking to go through, but let me not get into that. So you chop them up and chop them up until you have bounded size. When the pieces have bounded size, they are well-quasi-order. Any graphs of bounded size, if you have infinitely many graphs of bounded size, two of them are equal. So certainly one is contained in another. So no problem at that stage, and that's more or less the proof. You have to be a bit more. I've cheated again, but that's the idea of the proof. I guess that's okay. The rest of this is correcting some lies. So what have I've vaguely told you how the first statement is true. Now you can believe that the second statement is the same, except it's contests instead of tournaments. It's a bit more complicated because you have two kinds of vertices, left vertices and right vertices, and you have to preserve which is which and take care of them. But it's basically the same proof. This implies that this is actually true. I didn't cheat at all. I mean, if you can prove contests are well-quasi by immersion, it tells you that contests are well-quasi-ordered by switching containment. So split graphs are well-quasi-ordered by switching containment. But that's not what we wanted. We wanted rooted. We wanted to have, we got these by cutting this bounded cut set. We have to be careful about the bounded cut set. And I've ignored it. There's a bounded number of vertices that are special, that have to be respected. These are really rooted contests, and that makes it much harder. We can't prove this statement. We can't prove that statement for rooted contests. It may be true, but we didn't prove it. But we found a way to get around. And so there's another nasty step there that I don't want to talk about, but you can get the roots in, because we don't really need immersion. We're happy with round containment, which is a little bit weaker and easier. It's easier to prove things about. Anyway, okay, let me stop there. Thank you very much.